remembering here, in particular for the GRE. And that is that the reflection at this point here is n prime minus n over n prime plus n. Oops, yeah, squared. The Fresnel coefficient is n prime minus n over n prime plus n, with whatever sign is necessary to make it work. Okay? So for normal incidence, that's zero angle of incidence, normal incidence, the reflected intensity from a surface can be easily calculated. The transmitted intensity would be 1 minus that if you like, but I'll just write it 2n over n prime plus n squared. The Brewster angle can...
Is that squared for the reflected?
This is for the coefficients.
Oh.
So, no, for the Fresnel coefficients. For the reflection, they're both coefficients. I'm sorry that they're all called coefficients. For the reflection coefficient, it's squared. For the Fresnel coefficients, it's not. Fresnel coefficients include phase information. Intensity does not. Right? And the Brewster angle is equal to the angle whose tangent is n prime over n. Or, if you like, the Brewster angle is perpendicular to the reflected. This is actually what I should really write here is K transmitted is perpendicular to K reflected at theta v. 90-degree difference between the two directions. We have one other consideration here that you've heard about from optics in other courses, which is that if the transmitted index is lower than the incident index, so low index, high index, low index, going high to low. Number one, those signs switch, but then there's another important thing, which is that when we take a look at Snell's law, which relates the indices of refraction on the two sides, it'll turn out that we can't solve for the transmitted angle when n over n prime times sine theta I is greater than 1. There is no solution. And above those angles, so when we go out to a large enough incident angle, let's say from this side, what happens is that the wave that's incident upon the surface is totally reflected. If we solve for the electric fields in detail, which we won't do here, we actually would find out that for this wave that comes in here and a completely reflected wave, we would find out that there actually exists a little bit of electric field on this side of the surface. It tunnels, and it's called the evanescent wave. It goes through, it travels along the surface, and then takes the distance along the surface. And that evanescent field can actually be measured and picked up. It's experimentally observed. But over some distance, all of the wave ends up reflecting. It just leads to a phase shift. Okay. I probably have said this, but I'm going to say it again. Throughout the notes as I posted them, I try, when I have used a particular text as my source, or I think that that text is the best source for something, I try to just... You got them all? Mm-hmm. I try to just put a note at the top of the page as to what I used as my reference. And in most cases, you'll look through and you'll see Jackson, page 300, Ohanian, page 317, Griffiths, those are the main things. But in this case, my source is Bourne and Wolf, which I think is, the book has got a title something like Optics. And it is everything you wanted to ever know and not know about optics.
Everything you wanted to know and a bunch of stuff you can't understand.
Yeah.
It's not like it's a
For everything that I can tell, it looks to me as though Bourne and Wolf did everything right. There are no approximations, no. Or when they make an approximation, they say in giant, bold script, here we are making an approximation. Do not trust anything that goes beyond this. All right, so actually I've already said the next point that I want to make. But then I have a conclusion here, which is, this is from the point of view of someone who's actually had to do these calculations with complex indices, complex dielectric constant, right? And that is that MATLAB is magic. It makes it really easy to do Jones calculus, right? And but more to the point, you don't even have to tell it when something's complex. You take the square root of a negative number and it just gives you an answer that includes I. It might give you a little warning and say, hey, this is complex. You should know it, right? So it turns out you can create all sorts of matrices for multiplying Fresnel reflection coefficients by one another, and you can have a real and imaginary index of refraction. You can have negative index. You can put anything you want in there, and MATLAB just chews it up and spits out an answer. If you've done your coding correctly, it spits out the correct answer. So the hard part just becomes writing, the algorithm and making sure you've done it right. But you don't have to worry about what I just did over here, where I wrote complex index of refraction times sine of theta transmitted equals
Incident.
complex index of refraction, incident and transmitted. You don't have to worry about the fact that when these are complex, those are too. Well, actually, one of them, let's say, well, no. If both sides are complex, those angles do not have the meaning of normal physical angles. You can go in, you can dig in there and say, oh, here's what the physical angle is for this particular case. I won't go through that, but in terms of calculating reflectivities, Fresnel coefficients, phases, everything, you don't worry about it. You just plug the complex index into MATLAB and out spews the correct answer if you coded it right. Which in my experience is hard to do, but at least we've switched the problem from a conceptual physics problem to just making sure you've got the letters straight in your formulas. Okay. So now I'm going to talk about waves propagating in conducting media. Because everything that I've talked about here, I have included the possibility at a boundary that the index of refraction becomes complex, that something's going on there. And all the rules just apply, you just have to work it. But let's talk about what the waves propagating through conducting media might look like. Leave that up there. Now we're not talking about boundaries anymore. We're talking about the propagating waves. by spending more time here, I am probably shortchanging waveguides. And I'm sorry to those people who really, really wanted to study waveguides. If you do, you should take fields and waves. Because they will shortchange everything else that I've done in the course. All right.
Who teaches that?
Right now, I think it's Professor James Liu. And he was the one that convinced me to include a little bit of a lecture on magnetic circuits, because he actually is a physicist who went to the dark side and became an electrical engineer. And his PhD is in physics, actually, but then in his actual work, he became an electrical engineer.
He fell.
And he had said that he had not been exposed to magnetic circuits as an undergraduate, and then found use of them later on, and wished someone had just told him that this was a way of thinking about things. Not to be taught about it, but just to be told, here's a way of thinking about it, and then you go off and when you have a need, then you actually teach it to yourself. That's what you're all going to have to do anyway. All right. So, if I have an electric field in a conducting material, I'm going to get a current. That's going to change the Maxwell's equations that I'm allowed to use, or the relationships that I'm going to have in my Maxwell's equation. So I can write down that the current density is equal to the conductivity of the material times the electric field. That we did quite some time ago. All right? So Maxwell's equations become, in the absence, okay, so there's no free charge. All right? So the two divergence equations are still zero. I'm going to write down the two curl equations then. For the magnetic field, curl B equals my displacement current, which is what I would have had for propagation in vacuum, all right, plus 4 pi the current term.
And of course, these are in MKS.
Because this would be 4 pi j over C. Yes. What?
No.
No.
No?
These are CGS.
That's why there's a 4 pi.
Over C in there.
Oh.
Not a single Enon.
Or you know.
Yeah. Okay. That. I have no idea. I probably got that out of Ohanian. So it's got to be CGS. And for the electric field, curl A is the dt. Still no magnetic currents. All right. If we assume, let's just choose one region in space and assume that the electric field is oscillating. All right. Then my time derivatives become easy. Oh, and as a consequence, the magnetic field oscillates too. Right?
Negative sign.
What?
Lenz's law again.
Say what?
Lenz's law. Your negative sign.
Oh.
Faraday's law.
Okay. Okay. It's in my notes, actually. I just missed it. All right. So then that means that dE dt is e to the I omega t. And let's see, I've got to have an omega. I got to have an I. Good enough. I'm probably going to lose a minus sign in here somewhere. So these are Peirce-equal signs. There's that. All right, yes. So what I can do is rewrite this to solve for the electric field in terms of the derivative of the electric field with respect to time. And, well, I guess I could just plug the derivative in here, but that's not quite what I did. I went the other way. So that's fine. I have, if I did it right, 1 over mu curl B is equal to 1 over C epsilon plus I 4 pi sigma over omega, just making that substitution, if I did it right, dE dt. Okay, so I've got my old Ampere-Maxwell law, right? And I've got this extra term in here that comes from the induced current due to the presence of the field, all right? And because I've gone from E to dE dt, I've introduced a factor of I in there, right? But this sigma E was just the current. So what I've got is something that looks a lot like the old Ampere-Maxwell law in the absence of free charge, right? But it looks like this. 1 over C. Let's call this term epsilon with a tilde on it. dE dt. So now, if I have a conducting material, I am introducing a complex term into the dielectric function, and as a result, a complex term into the index of refraction. Yeah, okay. We actually do have to be a little bit careful here. Right, well, first of all, by the way, this could have been complex all by itself, because there could have been absorption in the material, right? But for now, I'm going to deal with a material which is otherwise non-absorbing, but just has free carriers in it. And next semester, either Professor Schroeder or I will talk in more detail about what happens when you have transitions between bands in solids and atoms and molecules that causes this part to be complex as well. But for now, let's just say we have a material that is otherwise simple dielectric, and then we introduce free carriers, and the carriers can move around in the material. Okay?
What class will that be?
Optical properties of materials, which is a 4,000 level course. You probably should have electromagnetic theory before you go into it. It won't hurt to have had optics, but it's not necessary. And you should have had a full history of World War II.
So basically,
It actually all depends. I have not decided who's teaching that course yet.
no, you said a full history of World War II. That means optics.
Right.
If he teaches it in the spring, sometimes you get a history of
Some
opera
of you
with
might have
it.
taken fundamentals of optics with Professor Key. Anyone? No. Okay. Good. Where was I? Yeah. So I got my complex dielectric function here, and I'll just remind you that n tilde, as I've used it over there, is equal to the square root of epsilon tilde, complex dielectric function, and that we have written that as n plus I kappa. And as long as I'm at it, I might as well also write that the complex index of refraction, complex wave vector is the complex index of refraction times omega over c 2 pi over lambda, all right? Which is omega over c n plus I omega over c kappa. We'll use that. So I'll leave those things, those relationships up there. All right. And All right, the solution to this equation and this equation simultaneously is an electromagnetic wave, right? So we get the wave equation, but we get a complex epsilon in there, and I've actually lost the. I'm going to write out the result. Apparently, I didn't write out the whole wave equation for myself, and I don't trust myself to get it right here. But let's just say that we are using this and this together. Then you take the curl and deduce the wave equation from that. And if you do it right, you end up with an effective velocity in these for the wave, which is the ratio of the square root of epsilon to the speed of light. Speed of light over square root of epsilon. But there might be a mu in there. I'm sorry if I have forgotten it. So, but you put those two together and you end up with the new wave equation. So that the solution to that new wave equation is always going to look like this. It's always going to look like E equals E naught, E to the I. How do I want to write it? N times omega over C times Z. That's the real part of the index of refraction.
5
What?
minutes.
Okay, whatever.
I'll just have to switch the memory card.
Minus omega t times e to the omega over c kappa z. It's always going to end up looking like that. But what dominates what? Which term is bigger, and whether it actually looks like an oscillating wave or not, or a decaying wave, or just a decaying something, will depend upon the ratio of kappa to n. Okay? So if n is much bigger than kappa, then you'll have a lot of waves as a function of z. And you'll just see those waves decaying. So the solution for n much bigger than kappa looks like this. That's supposed to be constant wavelength there, versus z. And for the other case, I've actually ended up changing the frequency here. For the other case, the electric field just decays. Okay? Well, you might have teeny oscillations in there. You might even get a cross through. But basically, it's going to decay before it has the chance to oscillate very much. So those are my two extremes, and I want to talk about what gives rise to those extremes. That's not a K. Epsilon, a new epsilon, is equal to the real part plus I times 4 pi sigma over omega. And how I relate n to omega and get my n and ik depends upon which of these terms is larger or smaller. Okay? So it will depend upon frequency, and it will depend upon the conductivity of the material. Okay, so I'm going to get rid of this and that.